After completing silicates and zinc phosphate, we move on to the next topic, which is zinc polycarboxylate. Polycarboxylate. So, this was initially developed by a Canadian chemist, a biochemist by the name of Smith. Yes, he did it in 1968. Now, what did he do? He took zinc phosphate cement and modified it. He took zinc phosphate cement and modified it. What did he modify? If you remember, in zinc phosphate, the liquid was basically phosphoric acid, H3PO4, right? The polycarboxylate, the phosphoric acid was now replaced by polyacrylic acid. He replaced it with polyacrylic acid. Now, what was the improvement that he did over here? If you remember, in phosphate cements, it was unable to have any chemical adhesion. When polyacrylic acid was introduced in the system, the polyacrylic system could now lead to adhesion. Yes, so the polyacrylic acid improved the adhesion property of polycarboxylate cement. Yes. Now, what were the basic applications? What were the basic applications? So, it was primarily used as a luting agent. Obviously, we were talking about luting systems till now. Therefore, it was used as a luting agent. It was also used as a base or a liner. It was used in orthodontics for luting band and bracket. Just exactly the same of zinc phosphate. But here you have a new function. It was used as a root end filling. It was used as a root end filling. Now, what is a root end filling? If you know that in a tooth there is a crown and a root, all the fillings that we have been dealing with was with respect to the crown, right? Was with respect to the crown. But all of us are aware that the pulp tissue extends all the way to the root of the tooth, and the filling that was given inside here, inside the area of the root canal, along with the sealer, especially at the end, that part was called a root end filling, the filling that is given at the end of the root. So zinc polycarboxylate was important over here. Once these applications were done and dusted, we now have to deal with the availability. How are they available to us in the market? How are they available to us in the market? So initially, what do we see? Our basic powder liquid. You can find it in powder liquid form. You can also find them as water settable cements. You can find them as water settable cements. Basically, what is it? The entire polyacid structure is freeze dried, and you can just mix it with water, right? The entire polyacrylic component is freeze dried, which means you have a cake of cement. That cake cement is freeze dried. You add a drop of water to it, it becomes the cement. Just like how you are mixing tang, right? You can just add water to it and it becomes a cement. Or you can have it as a capsule. How? Capsule powder and capsule liquid. You can mix two capsules, break it together, mix it together, and you can get a pre-mixed capsule. Okay. Now, water settable cement are the most important one, where you see freeze dried cement. You get freeze dried cement. So you get polyacrylic cement or polyacrylic acid, which is freeze dried, and when you add water to this particular component, you get the cement. So this is freeze dried cement. Now we can move on and come to the composition. you are coming to the composition. So let us look at the powder and the liquid component. So the first thing we will be dealing with is the powder component. In the powder, like earlier ones, we have a zinc oxide, you can have magnesium oxide, you can have other oxides, especially of bismuth and aluminium, and finally you have something called stannous fluoride. Stannous fluoride is basically a lead complex. So you have four components: zinc oxide, magnesium oxide, oxides of bismuth and aluminium, as well as stannous fluoride. Zinc oxide here is the basic ingredient. Okay, as usual, zinc oxide is the basic ingredient. Magnesium oxide is a modifier. Magnesium oxide is a modifier which aids in sintering. Magnesium oxide M is a modifier which aids in sintering. Then you have oxides of bismuth and aluminium in small quantities, in small amounts, and stannous fluoride. What does stannous fluoride do? It is very important. Why? Because stannous fluoride helps in increasing the strength. It helps in increasing the strength of the set cement. It acts as a modifier of the setting time, and phosphate did not have anti-karyogenic properties, and this was created by stannous fluoride because stannous fluoride gave this cement its traditional anti-karyogenic property. Right. So these are the powdered components. Zinc oxide, which is the basic ingredient, magnesium oxide, which is the principal modifier, also helping in aiding sintering. The oxides of bismuth and aluminium, which was added in small amounts to support these particular elements. Most important revolutionary element is stannous fluoride, which increased the strength, modified the setting time, and also gave the traditional anti-karyogenic property. Now, what did the liquid part of the polycarboxylate contain? The liquid contained an aqueous solution. It contained a aqueous solution of what? Of polyacrylic acid. It contained a aqueous solution of polyacrylic acid along with other unsaturated acids, along with other unsaturated acids. Which are these unsaturated acid? IMT. You have three acids, I, M, and T. I is itaconic acid, M is malic acid, and T is tricarbalic acid. Tricarbalic acid. So you have aqueous solution of polyacrylic acid, which is mixed with water. You also have other unsaturated acids. What are they? I, M, and T. You have itaconic acid, malic acid, and tricarbalic acid. So this is basically your composition. Now, how did you manufacture these things? How did you manufacture? So we are going to talk about the manufacturing. Okay, so the powder was taken, the powder was then sintered, sintered at a very high temperature, approximately about 1400 degrees Celsius. High temperature. You got a cake. This cake was then ground and you got powder particles. You got powder particles. Now let us look at the setting reaction. Setting reaction. Yes. The setting reaction. When you mix the powder and the liquid, the powder surface is attacked by the acid. Which acid? The polyacrylic acid. And from the powder, you are releasing three separate types of ions. You are releasing zinc ions, magnesium ions, and tin ions. Zinc, magnesium, and tin ions. They will now bind with the polyacrylic acid. They will bind with the polyacrylic acid which is present in the liquid, and they will link, they will create a polymer, they will create a polymer. Now how is the polymer formed? By producing links. Okay, and this link is called the carboxyl link, the carboxyl chain link. So you will have a set amount of zinc polyacrylate. The final verdict will be that you are getting a salt which is zinc polyacrylate. Zinc polyacrylate. So eventually you have landed zinc polyacrylate. So how does the structure look? You are going to have a core of unreacted what? Unreacted powder particles of zinc oxide. Unreacted powder particles of zinc oxide with an amorphous area consisting of zinc polyacrylate. Zinc polyacrylate. So this is the whole setting reaction. So what did we find? The powder and the liquid will now react. The powder will be attacked by the acid on the surface, leading to the release of zinc, magnesium and tin ions. These will be dispersed along the polyacrylic acid to form a zinc polyacrylate complex, which are linked together by the carboxyl chain, leading to the formation of a core of unreacted zinc oxide particles and a superstructure or a matrix which is made up of zinc polyacrylate hardened mass. So I hope you have understood the setting reaction. Now we move on to the conditioning. We move on to the manipulation of the zinc polycarboxylate cement. Okay, so unlike other cements, you have to maintain perfect condition of the tooth. This process is called conditioning of the tooth surface. You have to meticulously clean the tooth surface. Meticulous clean surface of the tooth is important. How do you do that? You do that by using 10% polyacrylic acid. You are going to use 10% polyacrylic acid. You are first going to apply the 10% polyacrylic acid on the surface of the tooth, and you will then rinse with water. You will then rinse with water. Okay, you can rinse with water. If you don't have water, you can use 1 to 3% of hydrogen peroxide, H2O2. So you're going to take 10% polyacrylic acid, apply that on the surface of the tooth. Then you're going to take your water syringe. You can rinse it off, or you can use 1 to 3% hydrogen peroxide in its place. Once you manipulate it, now you have to mix the cement, right? What are you going to use? You're going to use a glass slab. Obviously, you're going to use a glass slab. What glass slab? A cooled glass slab. Why? Setting temperature can or setting time can decrease over here. Okay. Now, what do? You are going to take a sample of powder, and you're going to take a sample of the liquid. Okay, the liquid should be dispersed just before you are going to mix. If you keep the liquid as is, it is going to thicken and become more viscous, right? So just before you start mixing, you have to put a drop of liquid onto the glass slab. And what you're going to do, remember in phosphate I told you it should be done in increments. No, here you are going to mix it together in bulk over a large area. You are going to mix the entire quantity over a large area. So you are going to use a stiff steel cement spatula. Stiff steel cement spatula, the instrument that looks like this, a stiff steel cement spatula, and mix the whole thing over a broad area. Once you have mixed it into a small homogeneous mix, you can then add further powder to this mix to get the correct consistency. until you get a thick consistency, until you get a proper thick consistency. Okay, so what all can we see over here? We can go on to the mixing time. How much mixing time can be given? You can give it approximately 30 to 40 seconds of mixing time. And how much time does it take to set? It is approximately going to take 7 to 9 minutes to set. Yeah, setting time can happen between 7 to 9 minutes. You can increase this further by either putting it in an air conditioned room or by cooling the glass slab. Okay, now one important thing is that, see, the cement should be used when the surface is glossy, meaning the surface must be nice and smooth and shiny. If the texture goes from glossy to matte, it means that the cement has become unusable. Loss of luster indicates that the setting reaction has progressed to such an extent where the cement has become non-usable. If the surface is shiny, if the surface is shiny, that is when you should use the cement. If it has lost the luster, it has become rubbery, you cannot use the cement. Okay, now when this cement is placed inside the patient's mouth, when the cement is placed inside the patient's mouth, it should be shiny. After the shiny stage comes the rubbery stage, right? After the shiny stage comes the rubbery stage. When it is inside the patient's mouth, you should never scrape the cement at this stage. It will lead to distortion or marginal leakage, right? When it is rubbery, you should never trim or contour the cement. After the rubbery stage, it will become hardened. This is when you should remove the excess amount of cement. Therefore, if there is a cement excess that is present over here in the rubbery stage, you should not touch it. Once it is completely hardened, once the cement has completely hardened, that is when you should eliminate this excess amount. This amount can be excess amount can be eliminated once the cement has hardened. Okay, now what are the advantages of this? We know that it is lesser pulp irritating and it has significantly good adhesive properties. Therefore, increased adhesion is present at the surface of the tooth. And finally, disadvantage. It has limited fluoride release. It is better than zinc phosphate cement, but polycarboxylate have limited fluoride release, therefore limited anticarcinogenic properties. However, it is better than zinc phosphate. Therefore, polycarbs are much better for luting. This was later solved in glass ionomer cement. So that's where we will see the next anti-karyogenic property. This was the entire information you require for zinc polycarboxylate cements. We shall now move on to zinc oxide eugenol cement in the next session.